deriving the boundary conditions for electromagnetic fields across the interface of two media, right? So suppose we have two different medias, and we want to understand how the electromagnetic fields change as they pass across these two media. So we have one medium with permittivity and permeability epsilon 1 mu 1, and the other media with permeability of epsilon 2 mu 2. And we want to know, given an EB field, how that E and B field are related, side 1 versus side 2. And how we're going to do this is we're going to utilize Maxwell's equations, which I provided over here. So first we'll use Faraday and Ampere's law by drawing our classic Amperian loop. So if you don't know what this is, you can see how in Faraday's law we take a closed line integral of our electric field, and that equals the enclosed change in the B field with respect to time. So what we do is we draw this closed loop that our electric field will be acting on. And you'll note that our electric field has both a normal component, or a perpendicular component, and a tangential component, like this. And what we'll do is we'll analyze how this Amperian loop behaves and we have side W and side L, and we'll see how it behaves as L approaches 0, that is, as we get really skinny and we reach very close to the center at this interface. And what happens is that once the area gets really small, there is no B field. There can't be any B field that it's possible to enclose because there is no area there. And so we can set this equal to 0. We can also note that there is no W, there is no L, and so because of that, no work is done by the electric field on these sides, and all the work is done on the tangential component. So we can rewrite this then as E parallel times W minus on side 1 minus E parallel on side 2 times W equals 0. And you'll see that this boundary condition is independent of W, so that E1 parallel equals E2 parallel. And this is our first boundary condition that we have derived using Ampere's law. We can do, I'll leave this up to you guys, but we can do a very similar thing with Ampere's law using the loop again, where when the loop's area goes close to 0, this term goes to 0, leaving us with H sub 1 parallel minus H sub 2 parallel equals 0. And then now for our normal components, to find those, we have to do something different. We have to use what's called our Gaussian pillbox. So suppose, once again, we have side 1 and side 2, and we draw our Gaussian pillbox like this, with length L and area A, and with a normal component and a tangential component. Well, what we're going to do is, again, we'll take we'll take the limit as L approaches 0 so that this term goes to 0, leaving us with just this surface integral of d times d sub 1 perpendicular minus d sub 2 perpendicular times a equals 0. You'll notice that for I guess this would be the other way around, the minus sign, but you'll notice that here the electric field is coming out of the pillbox, whereas here it's going in, which is why we have this minus versus this plus. And just to clarify, what we're doing here is we're calculating the flux, and so because we've been able to simplify our system so much that L goes to 0, so that we're dealing with this Gaussian pillbox, we're able to write this very simple expression that describes how the electric field changes across a media, how the normal component of the electric field changes across the media. And once again, you can do a very similar thing. You can do a very similar thing for the B field to calculate that B sub 1 perpendicular minus B sub 2 perpendicular equals 0. And these are our two other boundary conditions. These four make up the boundary conditions that explain everything we need to know about our electric and magnetic field. Now, one very important special case I want to walk us through is here we're dealing with media, finitely conductive media, right? That is, these are potentially lossy materials or lossy materials. They're not conductors. They're dielectrics, or they're vacuum. So what happens when one of these sides, and this is very important because constantly when you're doing electromagnetic theory, you're dealing with metals, which are perfect electric conductors. So it's very important for us to understand what happens when one of these sides is a PEC, a perfect electric conductor. Now, to answer this question, we need to ask, what do we know about perfect electric conductors? We know that the interior of a perfect electric conductor has no electric field and has no B field. Or really, no electric field and no B field. But we do know, and so we can say that E sub 2 and B sub 2 are equal to 0 respectively. But what we do know is that any currents and charges that are in the dielectric all end up on the surface, right? Our Q E sub S and our K sub S, where K is our charge density and Q is our Q is our charge density and K is our current density. You'll be familiar with the fact that all the charges in a perfect electric conductor all end up on the surface of the conductor because that's where it's most. You can derive this yourself, but that's where it's most efficient for. That's where they minimize energy, being directly on the edge of the perfect electric conductor. And so we still have our side 1 with epsilon 1 and mu 1, like this. And so looking at our boundary conditions that we've written, we'll notice that we can't simply just say that this equals 0 and say that this equals we can't just say that equals 0 and this term also equals 0, because we know that there are actually currents and that there are charges at the surface, so that even when we take L to approach 0, there is actually something going on there. And so instead what we can do is we can write this, for a perfect electric conductor, actually I think it'll be easier if I just show you down here. I've provided all of the equations. You can see, and I'll write it in the notation that we've been looking at so it makes more sense. But E1 parallel would equal 0, E1 tangential, but H1 tangential now has that K component I was talking about, the surface current. You'll notice that the side 2 terms go to 0, as I had mentioned already. And similarly here, because of those surface charges, epsilon 1 E sub 1 perpendicular equals whatever the electric charges on the surface. And our magnetic field perpendicular equals 0 because, and this should be a 1 for the scenario that I drew out up here, and that is because B sub 2 equals 0, and there isn't any other terms in the magnetic Gauss's law, so that means that B sub 1 perpendicular would have to equal 0 in this situation. And so that's a walkthrough of the boundary conditions for electric and magnetic fields for both finite conductive media, as well as if one of the sides is a perfect electric conductor. This is going to be very important for our future videos, where we start to discuss waveguides and resonant cavities and electromagnetic waves and the different geometries they can take. Because, as you know, whenever we solve a partial differential equation, like the wave equation, which we'll have to do for electromagnetic waves, we always need boundary conditions to help us in addition to our differential equation that will allow us to come up with the solutions. And so these boundary conditions are very important for establishing the geometries of what we're dealing with, whether it's a waveguide or a resonant cavity. And so you'll see how we'll use what we have derived today in deriving the solutions for various electromagnetic wave configurations. Thank you so much for watching. If you enjoyed, please like the video, and please feel free to comment anything that might be of confusion. In the comments, I'll be sure to respond. Thank you so much.